We're going to understand the concept of the parallelogram law for adding vectors, as well as the triangle law. I'm going to understand what a zero vector is. That's going to be mentioned. And the difference between two vectors. How do I subtract vectors? And representing a single vector as a combination of two or more vectors. And I'm going to apply this to problem solving. That's basically the gist of what I want to try to get through today. So let's get started. How do I add two vectors? The sum of two vectors can be found in one of two ways. There is the parallelogram law, and you can see that I have two vectors here, A and B, and I can put them tail to tail, as you see in this diagram. So here's vector A sort of pointing up and to the right, vector B pointing down and to the right as well. Putting them both together, I can actually represent the sum of those two vectors as this side here, which represents the diagonal between them, right? So here's A, here's B, and they're joined together at the tail. Remember, we talked about tip and tail or head and tail before. And if we just sort of complete the parallelogram between them, so put another vector B up here, put another vector A over here, and complete the parallelogram, then the sum of these two vectors is this diagonal that is between the two sides that are joined at the tail right here. That's what this sum represents. The dotted line is the sum of those two. So the parallelogram law is useful for subtracting vectors as well, because we can do A minus B, which I'll show you, I'll demonstrate to you in another slide. But here's how we sum two vectors, by just simply taking the diagonal between the two sides that are joined together by their tails and completing a parallelogram. That's one way that we can represent the sum of two vectors. Okay, so the other way is what we call the triangle law. And the triangle law says that if I take the head of one vector, so this vector here, and connect it to the tail of the other vector, so this is vector B, so I'm trying to add vector A and B again, then I could still represent the third side of this, which would complete the triangle, as being the sum of those two vectors. Now the difference is that I'm starting here, and I'm going up to here, then I'm moving from here and continuing on to this endpoint. So really what I'm saying is I started here and I ended here. So that's why this represents the sum of the two vectors. So it's like a trip where you start at one point, you go on a journey up to some third point, and then, sorry, some second point, and then you continue from that journey to the third point. Well, really what you've done is you've gone from this starting point to that ending point. So the tail of one vector to the head of the second vector represents the result of adding those two vectors together. So that's a triangle law approach to it. All right, so the parallelogram law and the triangle law basically end up being the same thing. One is a diagonal and one is a third side of a triangle. All right, so let me give you some examples of using that parallelogram law. Here are two vectors, U and V. I'm putting this to represent my U. I'm using this to represent my V. I want to show you what the sum of those two vectors could look like. So I'm going to take this U, which is on this side, and I'm going to duplicate it over here. Now remember, these two vectors are equal, right? They're equal because they have the same length and they have the same direction. So to represent this as my U vector, either it's not in the same place, means the same thing. So here's my U vector here, here's my U vector here. Here's my V vector down here. So I'm going to put another V vector up here. So I have a U and a V that I'm adding together, and I've completed the parallelogram by putting another U here and another V here. And I'm going to represent the result of that with this red vector, that diagonal that goes between those two. Now notice the direction of them is going from the tail of the two vectors, right? That's where the tail of the resulting vector is as well, up to the point which is represented by the two other vectors' heads put together right there. So there you go. That's one way to interpret the sum using the parallelogram law. We could do the same thing with subtraction. Now here's the difference. Here's my U going from tip to tail, right? Or from the tail to the head. And then I'm going to put my V, right, which is normally going this way. I'm going to put it going this way because the opposite vector is just a vector that has the same magnitude, but just runs in the opposite direction. So here's my U, which is the first part of this vector calculation, and I'm minusing my v. So I'm going to take the v vector that I would have added the last time and I'm subtracting it. Let's make it go the other way. So instead of going this way, it goes that way. Okay, let's complete the parallelogram. I'm going to put the u back here, and I'm going to put the other minus v at top here. So it means that the result of this would simply be this diagonal running from here to here. Right? So the other one that we did before, the diagonal was a longer diagonal. This is the shorter diagonal between the same two. So if I complete the parallelogram that we had before, where I had the u and the v and I was adding them together, and I was saying that this line was the result, now I'm subtracting the v from the u, and it turns out that that gives you a diagonal that runs from here to here. Well, you can look at it in either one of these two parallelograms. But if you think of it in terms of the triangle law, it's the same thing, because you start off here. So you start off here going from u from this side of the u to this side of the u, and then you're going here, which is the minus v. So it really means you're going from here to here. That's really the result of the motion that you've just taken. You started here, you went along u, which is a positive direction, then you went along v, which is a negative direction, and that result means that you went from here to here. And it means the same thing as if you looked at the first parallelogram and just simply took the other diagonal. So the first diagonal went from here to here. The second diagonal went from here to here. It's the second diagonal. Now, if I were to do this the other way, now let me just take you back a second. This was u minus v. And you ended up with this vector going from here to here. What if I did v minus u? Well, I'm going to go through the same process. Here's my v, and I'm going to minus my u. Now, here's what the u normally would be, going from here up. But if I reverse the direction of that u, I'm going to be going from here down. That's my minus u. So I'm going to complete the parallelogram by putting another v here. And that represents the track, which goes from here, the minus here, and the positive here. That track goes from here to here. So again, I'm getting that other diagonal that was in the original parallelogram. But the difference is between this one and the one before is that if you remember, the one before had the diagonal that was running in this direction from here up to here. Because I've reversed the difference and I'm subtracting it the other way, although it's the same diagonal, it actually runs in the opposite direction. Hopefully that makes sense. And I'm going to move on. So the diagonal that runs between these two that goes from here to here is the u plus the v. The v minus the u is the other diagonal running like this, but if it was the u minus the v, it would be the same diagonal but running in the opposite direction. Okay? So a vector sum is sometimes called a resultant. Again, just some terms that we need to know. The vector that's equal in magnitude but opposite in direction is referred to as the equilibrant. So it's like the thing that would take you in the other direction but has the same magnitude, the same length. That's what we call the equilibrant. Adding two vectors that are opposites give us the sum equal to the zero vector. So if I added the equilibrant and resultant, I get what we call the zero vector because they cancel each other out. And sometimes you refer to the zero vector with a zero with the arrow on top of it. That just means a zero vector. You can also multiply a vector by something called a scalar. So if I took a vector and multiplied it by a number, then I would have k times that vector. And that would either make the vector become longer or shorter. It's still going in the same general direction, right? But it would either be longer or shorter unless the k is negative, which is less than 0, which would mean that it would not only be longer or short, but it could also be going in the opposite direction if it was negative. Let me give you some examples of what that might look like. I'm going to run a little video with these three vectors. I have three vectors. There is an A, there is a B, and there's a C. So you look at the way the vectors are running and their various magnitudes. I'm going to take the A, which is this vector, and add it to two of the B's. I'm going to take the B and I'm going to multiply it by a scalar, which is going to make it a little longer. Then I'm going to take two of the C's. I'm going to add everything together, and you can see what that result looks like. So I'm going to run a little video of me doing this using the smartboard, and we'll see what that looks like. So here comes the A. And then I'm going to add to that two of the B's, right? So I'm putting that on the tip of the vector. So that's one B. And that's the second B. So I've added on two of the B's. Then I'm going to add on two of the C's. So that's one C there. and the second C right there. So what's the result of all of this, right? What is the actual resultant vector? Well, here it comes. It's a vector that starts off at the beginning of the first vector and goes to the end of the last vector. So there's your resultant vector. So that's the A plus 2B plus 2C. All right, let me do a similar one. Now, this one has a minus D at the end. So I'm going to take a plus A. I'm going to take 2 of the B's. I'm going to take 1 C, then I'm going to minus a D. Now, here's what D is. D runs from right to left. Or what am I saying? Is that right? Yeah. No, left to right. Left to right, right? It runs from left to right. So a minus D just simply would be a vector going the opposite direction. Right? So if it says A plus B plus C minus D, I'm going to take this A, this B, this C, and take the opposite of the D. So here it comes. So there is your A. I'm going to put the B twice. Okay, that one isn't lined up so great, but anyway. I'm going to put one of the C's. And as I said, we're going to put a minus D. So not the D, but the minus D, the one that runs in the opposite direction. So the resultant vector is that vector. The vector that starts where the first vector started from and ends where the last vector ended. Okay? All right. So time for us to answer some questions based on what you just saw. And I'm going to be throwing it out to the room, so I need some input now. This box, this rectangular box, rectangular prism, has 3 vectors in it. So OA, starting at O, and going to A, we're going to call that vector A. This one came from the textbook, by the way. OC runs from O to C. We're going to call that vector B. And OD, so from here to here, we're going to call that vector C. So those are 3 vectors within this rectangular prism, this rectangular box. And you can see various letters on each of the vertices of this rectangular box. So what we're asking for now is each of the following. BC. Now, BC clearly runs from where you see the B right here to the C over here. So which vector could I use to represent my BC? And again, I'm asking you, so I need your input at this point. Where is the BC? What could I use of the A, B, and C to represent the BC line going from here to here? Just using the vectors A, B, and C to describe the length going from B to C. What do you think? Anybody?
A, negative A.
There you go. She's absolutely right. It's negative A, but not A, because A runs from O to A, but negative A goes in the other direction. Okay? All right, GF. Let me get a GF from somebody. So G is here, F is here. What would GF be this time? Do I have to call people's names? Let me see what we got here. Sorry, I didn't get that. Could you see? Perfect. It's actually A, and it's A this time in a positive direction. How about OB? So I'm trying to get from O to B. So here's O here, here's B here. How can I get from O to B? Now think about what we just saw in the previous slide and give me some vectors that could make that magic happen, going from O to B.
A minus B.
A minus B, you say, to go from O to B. If this is A and this is B, I think we should actually add them together, if you see what I'm saying, because I need to go in this direction and then that direction. So I wouldn't use minus this time, because to get from O to B, I'd add A and then add B, because this goes in this direction, that goes in that direction. All right. How about AC? So close, but not quite. How about AC? Now to get from A to C, I need to go from here to here. So how can I make that happen? A to C, by adding vectors A, B, and C together. I need to start here. I need to end up over here. Well, how about we do this? Say it again.
B minus A.
Well done. right? Because to get from there to there, I could go, remember, I'm trying to get from A to C. So I could go, remember what A and B and C are, right? I'm trying to get from here to here. I need to go in a negative direction for A, right? Which is the minus A here. Then I need to go in a positive direction for B, and that's what that is. I could actually go this way as well, right? I could go B here first, and then I could go minus A, which is the same thing. I mean, the result is the same. Okay, hopefully we are kind of getting the hang of this now. How about BG? I need to go from B up to G. How can I make that happen?
Is this C minus A?
Okay, so let's see what you're saying. Now, if I need to get from B to G, you're saying I'm going to go C, which is going from B, which would be going this way. Sorry, C would be going forward this way. I'm not sure if sorry, you said, give me that answer again. Sorry, because maybe I didn't hear it right.
I said C minus A.
C minus A? Let's see. Okay, perfect. Yes, C minus A is right. Yeah, I just realized that you were saying it the right way. You're perfectly right. Okay, so I'm going to get from B up to G. So if I went in a minus A direction, which is this way, and then I went in a positive C direction, that would take me from B to G. One more, OF. Last one. O to
A
F.
plus B plus C.
Let's see now. O to F. Yeah, absolutely. A plus B plus C. Well done. There you go. All right, let's move on. Now, this is going to get a little bit more involved because now we're going to have to get back and start looking at some trigonometry, right? Hopefully you have your calculators nearby. I'm not going to explain every single step in detail because some of it I'm hoping you will just sort of remember from what you did in grade 10 when we were doing trigonometry. So this takes some grade 10 trig. What I have is a diagram. Two forces are pulling on an object. F1, which I've labeled here, and by the way, I put these red lines here to represent east, west, north, and south, which we'll talk about in a minute. F1 is a magnitude of 10 newtons, and F1 is pulling, sorry, what am I saying? F1 is a magnitude of 10, F2 is a magnitude of 20. F1 is pulling the object south, and that's why using the north-south line, so north goes up, south goes down, west goes left, and east goes right. That's why this is going down 10 newtons. So somebody's pulling, or some force is pulling 10 newtons in a southerly direction. That's my F1 force. Newtons, by the way, is what we're going to be using a lot when we're talking about the magnitude of force. The F2 is pulling with a force of 20 newtons. And it says here that it's pulling in a north 23 east direction. We're reminded about something we talked about on Wednesday. North 23 east means I'm 23 degrees away from north on the eastern side. So here is the eastern side. Here's my north-south line. And I'm 23 degrees away from that. So I'm in this, what you could call, I guess you could call it the first quadrant if we're using a Cartesian grid sort of reference. This is 23 degrees away over here, right? What I'm asking for using, no, this is not drawn to scale. So please, I'm not saying this line is necessarily twice as long as this. In reality, it's supposed to be because this is 10, this is 20. So there's a 23 degree line over here. There's a 20 Newton magnitude force pulling in this direction. And there's a 10 Newton magnitude force pulling in this direction. That's what we have. So think of this as maybe being two ropes being attached together at this common point right here. One person is on the end of this rope, and this person is twice as strong for whatever reason as the other person. Maybe there are two people on this side. And this person over here is able to pull with a force of 10 newtons. So we're asking, if one is pulling this way, one is pulling this way, where are we actually going to be heading? What direction are we heading in? And what force is that going to have? What's the resultant force? So what I'm going to do is I'm going to fill this in by putting in some other vectors. So there's a vector that's going down by 10. So I'm going to put a vector going down by 10 here as well. So let's imagine this as being another 10 newtons over here. I'm going to put another vector over here that runs from here to here, which would represent the same vector as this 20 Newton vector over here. So I'm taking a vector and another vector to create, or what I'm really doing is filling in the parallelogram that we talked about when we're using the parallelogram approach to this. And what I'm going to do now is put in the line that represents that resultant. We don't know how to calculate anything yet. I'm just going to put that line in. This line that I just put in is what we talked about when we were looking at parallelogram law earlier on. It's the diagonal between where these two vectors meet. If we're using the triangle law, then we could say that this vector goes from here up to here. This vector goes from here down to here. So the resultant vector has this starting point and this ending point. So if that picture helps you to understand where we are, now let's get to how we can do some actual calculations. I'm looking for the resultant. The resultant would be this vector. And I'm looking for the equilibrium. The equilibrium, we said, was just simply a vector that pulls in the opposite direction with the same magnitude. That's all that is. We'll get to the equilibrium later. Let's talk about the resultant first. How can I figure out the length of this line? That's really what I'm after. There's a 23-degree angle out here. That shouldn't be too difficult for us to come up with the angle that's inside here then, right? Can anybody tell me what the size of this other angle that's on the other side? This is a straight line, obviously. It's a north-south line, so it's a straight line. What about the angle in between these two vectors here? How could I get that angle? That's a fairly simple proposition, I would think. What would be the size of that angle inside here? This angle right there. Anybody can tell me what that would be? Just think back to your trigonometry from grade whatever. No. What's this angle right here? One on the inside of between the two vectors that we're trying to find this diagonal, but what is this angle inside here? Anybody? How am I going to get that angle? Hello?
Is it 157 degrees?
How do you get that?
I just subtracted 180 from 23.
Absolutely. So that's a good start. This is a straight line, 23-degree angle on the outside, and 157 inside here. But here's what we're going to always do when we have the angle between two vectors that we want to find the sum. I'm actually going to focus not on this angle inside here, but this angle up top here. Now, I'm going to remind you of something with parallelograms. Two adjacent angles in a parallelogram are supplementary. What that means is that they add to 180. So if this is 157, which is correct, by the way, then this would be what you have left over from 157. The truth is that we could actually also make the inference that these two angles are equal because they are what we call alternate angles. This line that's coming south and this north-south line, those two lines are parallel. This would be what we call a transversal. So this angle here is actually the same as this angle over here. Okay, now, can we use the size of this angle along with this side and this side to find the length of that side? I'm not going to put anything on the screen until somebody thinks back to grade 10 trigonometry and see if they can remember. If I know the angle in between these, I'm trying to find this dotted line right here. That's my goal. I want to know how long that line is because that line is the magnitude of the resultant force. But I know this angle is 23, what I'm pointing to right here. I know this line, same as this line down here, is 10. This line is 20. So I have this angle, I have this side, I have that side. I'm trying to find this side over here. Think of something you learn in trigonometry that I could put together to find the length of this line. We're going to call this line here or x. Can anybody think of any law in trigonometry that might help us to do that?
Can you use sine law?
For sine law, if I was going to use sine law, then I would need to know an angle opposite to a side that I know. I know this angle. Sorry, I know this angle. I know this side, I know this side. I have the angle between them. So this is the angle x, not angle, sorry, this is the side I'm trying to find. This side I know, that side I know the angle between them. Here's what I'm going to suggest. Let's use a cosine law. Cosine law would say that this x here, right, we'll get to this angle theta in a minute because that's going to give us the direction that we need later on. But this angle here, sorry, this side here, right, is equal to this side 10 squared plus this side 20 squared minus the 2 times the 10 times the 20 cosine of the 23, which is the angle between those two sides right there. Right? So in this case, I'd have to say the cosine law will be the one that kind of would be more applicable. So I don't need to teach you the cosine law. That's stuff you learned back in grade 10. I'm just going to continue the question and tell you that when you do all the math from this, you have to find a square root eventually and all that good stuff, that this worked out to be 11.48. And that's also in newtons. So if this is 10 and this is 20 and that's 23 degrees between them, then using the cosine law, I'm getting 11.48 newtons. So here's my statement. The resultant force, right? The force that you're going to be pulling with on this line right here, if this is 10 and this is 20, and this is 23 between them, is 11.48 newtons. That takes care of one aspect of the question. But a vector, which we learned yesterday, doesn't have just magnitude, it also has direction. So we need direction, and for me to get that direction, I need this angle right here. This angle that's inside of this triangle that we just created by putting this diagonal inside here. I need this angle right here. Because if I have this angle, then I can actually now give the resultant angle as being the sum of this plus this. Because remember, this represents the resultant line. The angle that we really ultimately want is this angle from north all the way around to here for us to be able to give the answer as some angle that's some degrees to the east of north. But we need to start off by getting this smaller angle right here. I'm going to tell you what you know. We know that this side is 20, this side is 10, and we also now know that this side here is 11.48. Now we could use the cosine law again, because when you have all three sides of a triangle, you can use the cosine law. But I'm going to use the sine law because I find the sine law easier to work with. I'm going to say, follow me now, that the sine of this angle here over the side opposite to it, which is 10, it's not exactly equal because we rounded this 11.48, is approximately equal to the sine of the 23, which is this angle up here, over the side that we just found. Am I going too fast for us? Do we need to say that? Let me go over that again. I'm looking to find this angle inside here. This is what I'm trying to find. This angle right here, the one I'm pointing to, the theta degrees. So I'm saying that the sine of this, using sine law, over the side opposite to it, which is 10 newtons, we're just going to call it 10, is approximately equal to, the sine of 23, which is this angle right here, over the side opposite to it, which is 11.48. Let me let that sink in for 10 seconds. If that is true, then I can work out what theta is. Theta is approximately equal to 19.9 degrees. Now, that's just this part right here. But if I'm going to give a direction, look at how I got the direction the first time. The direction was north 23 east. So from here to here was at 23 degrees. Now we've been sort of moved further to the east by another 19 degrees, 19.9 degrees, almost 20 degrees. So it must mean that where I am now is the 19.9 plus the 23. So I'm now 43 degrees to the east of north. So what's my answer? North 43 degrees east. That's the resultant direction when I take this theta angle, add it to my original 23. The key to this is having a good diagram. Let me just be honest about this, right? Being able to draw the diagram makes a big difference. So I'm going to stress that one of the things you want to get practice on is drawing the diagram. So here's the 23. Here is the 19.9. I'm rounding this up about 20. That gives me the 43 degrees right here, approximately. So the direction of the resultant force, just to answer the question with statement, is north 43 east. The resultant force has this magnitude, 11.48 newtons, and has this direction. Okay? Now it asks for the equilibrant. That's easy. I'll tell you why that's easy. The equilibrant would be a line that goes in the other direction over here, has the same magnitude, right? So it has the same magnitude of, what is this, 11.48 newtons, but its direction would be the opposite direction. So this is north 43 east. This is going to be south 43 west, because it's a line. So this dotted line that I'm pointing to here is just going to be over here. I probably should have put this in when I was doing my presentation. It's just going to be a line that's over here, the same angle away from this, what is this, the west line, that it is in this quadrant over here. So it's really just the opposite. Instead of north, it's south, and instead of east, it's now west. So whenever you have to do an equilibrant and it's set up this way, like northeast or whatever, just take the opposite for the equilibrant. That's simple. All right, let's get to this one.
Mr. Koenig.
Yep.
For the question, this question,
Yeah.
I used the physics method and I got the same answer.
Oh,
Like,
then
I've done
use a physics method in that case.
Is that okay?
Oh, absolutely.
Okay.
And the beauty about math is that you can take a lot of different routes to end up at the same place. So you go right ahead and use whatever you learned before. If you find that to work easier for you, then you go right ahead. Okay. All right. Now the question that's similar. F1 has two forces are pulling an object. F1 has a magnitude of 7 newtons. All right. So here's my F1. I've labeled it on my diagram. F2 has a magnitude of 11 newtons. There's it on the diagram. The difference this time is that they don't give us a directional bearing. They tell us the angle between F1 and F2. Between F1 and F2 is 135 degrees. That's what it says. So these two forces are being pulled in both directions. One going this way, one going this way. There's a 135-degree angle between them. And we're being asked to find the magnitude of F1 plus F2 and describe its direction relative to F1. So sometimes when you're asked for direction, you can give the answer not in terms of directional bearings like north, south, east, or west, but you can say it is this number of degrees away from one of the previous forces. And that's how we're going to answer this question. So again, my diagram is here. I put that resultant vector as the diagonal between the two previous vectors, the 7 Newton vector, the F1, and the 11 Newton vector, which is the F2. The diagonal between them would be a diagonal that probably runs something like this. I put in the other two sides as well, the parallelogram. So I dropped the 11 Newton line over here. I dropped the 7 Newton line over here. And the diagonal would therefore run from here to here. Okay, so the other thing that we need to recognize is that the length of this side, we use the cosine law again, right? The cosine law, but I need the angle that's the supplemental angle up here to use the cosine law. It's useless for me to use this angle to try to find this side. I need this angle that's over here. And this is a typical way that we do vectors. Instead of using the angle between the two vectors, we use a supplemental angle. So I'm going to take the 135 away from 180 and label this angle up here as being 45 degrees. And now I can use my cosine law to answer the length of this side x over here. So here's my cosine law. X squared is equal to the 7 squared plus 11 squared minus 2 times 7 times 11 cosine of 45. We know how that works. And again, skipping a couple of steps, x is approximately equal to 7.82 newtons. So the resultant force, the magnitude of this force, right? This force that is the resultant of these two previous forces is a 7.82 Newton force. But what is its direction relative to F1? So really what I'm asking is, what is this angle right here? That's the angle I'm trying to find. How far away? I'm not trying to ask you, how far is it from north, south, east, or west, or anything like that. I'm trying to ask you, how far is it from one of the previous forces? What is this angle right here? Well, how about if I use a sine law? Oh, by the way, the force there, I'm just giving a statement here. I don't know why there's a comma there. It should have been a period. Anyway, so let's get to the sine law. The sine law would say that the sine of this angle I'm trying to find, so the smaller angle, not the 135, the 135 is a big angle. The sine of this smaller angle right here over this side, which is the 11 Newton side, is approximately equal to the sine of 45 over what was the x, but we know the x is now 7.82. So we can now finish that calculation and say that theta, which is the smaller angle, now remember, I'm not looking at the big 135, I'm looking at the angle inside here. That is 84.1 degrees away from F. So this line is 84 degrees, 84.1 degrees away from the 7 Newton line. And that's the end of that question, right? So I've given you how long the line is, or the magnitude of the line. I shouldn't say how long, the magnitude of the line. I've also given you its direction, but relative to one of the previous lines, the F1 line. Okay, last question. This one is a sort of a very typical and probably the kind of thing that you would do in your physics class. Sounds like you've met a lot of these kinds of things in physics before. The difference with this one is that I'm going to use the direction from the north line going clockwise. So plane is flying in Kamiar at a speed of 420 kilometers per hour. So the 420 kilometers per hour is in the direction of 291. What that, oh, shouldn't have gone there yet. Hold on. So the 291 is the angle that goes from north all the way. So it's going to go past 90, starting at the north is 0, going past 90, going past 180, going past 270. 291 will be in this, I guess you'd call it second quadrant right here. And that's where the 291 is. Starting from here, it's 291 away from north, going in a clockwise direction. Now, wind is blowing from the north. So from the north means the wind is blowing south. So that wind is actually going south, from the north to the south. So it's going down. So again, I put in all of the equivalent vectors to form a parallelogram. So this is my north-south line, which has a 50 kilometer, and I'm sorry I didn't label these with all of the numbers, 50 kilometers per hour going this way. This one is, what is this, 420 kilometers per hour going that way. I put another vector going down here, put another vector going up and to the left here. And that means that this line represents my resultant velocity. So let's see if we can put this into perspective. What angle do I know? Well, I know this 69-degree angle right here, if you think about it, right? 69 degrees here because I took the 291 away from 360, and that's 69 degrees inside here, which would mean that this angle up here, again, two parallel lines, parallel line here to this line here, this angle is 69, this angle over here is 69 as well. So I can use the cosine law again. So that cosine law will allow me to get this line right here. So again, I'm not going through every single step. You've done cosine law from grade 10. This works out to be 404.78 kilometers per hour. That would be the resultant ground velocity. Well, speed, really, not velocity, but we have to get direction as well.
Mr. Kamek,
Yeah,
I
go
just
ahead.
have a question.
Yeah.
In grade 11, we learned that the angle, like any angle, usually starts from the east and then goes counterclockwise. So how, like the 291 that
Okay.
you said starts at
Yeah.
north.
Yeah. So later on when we're doing summing vectors, we're going to be using that convention as well. But if you're talking a directional bearing, then 291, if they say 291, they do mean measuring from north and going in a clockwise direction. So we have to, unfortunately, go that convention for this question. But I know what you mean, starting from 0 on the east, and then, yeah, I do know that convention, and we'll get to that at some point. But at any rate, so 291 measured from north takes you all the way over here. So now you're going in this direction. We added the two vectors to give it a parallelogram. So the dotted line represents the resultant, and we said already that we can use that to find the length of this line, which would represent the speed of the plane, and that works out to 404.78 kilometers per hour. Now, our goal now is to figure out what this direction is here. So I need to know what this angle is right here. Right? What is this angle right here? Because I know this is 69. If I could figure out what this angle is right here, I could add it to 69 to get what the overall bearing is now, because that would mean I could start from here and go all the way around to here, right? So let's see if we can do that. the sine of theta, and by theta I'm talking about this angle inside here, over 50, which is this side here, is equal to the sine of 69, this angle here, over the length of this side, which you said was 404.78. So that works out to be approximately 6.4. So this angle inside here is 6.4. So what am I going to do with that? I'm going to actually take that away from this original, remember, this whole thing here, from here to here was 291, right? That was 291 measured from north all the way around to here. But I need to take off this little piece here to see how far, what is this bearing, which is going in this direction. So I'm going to take off that 6.4. It gives me approximately 284.4 degrees. So this represents the bearing that I'd be traveling on with a speed of 404.78 kilometers per hour. So again, the diagram is really the key to this. That's really, the thing that is going to help you to put all your dimensions and your angles and so on in the right place and take the right approach. So I know this is a pretty involved, class here compared to the previous one, but that's the way that goes. That's the way that goes. So unless there are any questions to this, that is it from me. I didn't put any statements for this one, but that's basically what I wanted to go through today. You should be able to handle the homework questions based on what we just did. All right. Is there anything that anybody wanted to ask about what we did today? And yes, anything you learned from any other class, like in physics, that you can apply to this, then by all means, you go right ahead and use that. I have no objection to that whatsoever.